Hi everyone, what's up? Welcome back to my tutorial channel. Daniel's here and today I continue to work on graphical summaries. So the last video I only showed you how to summarize qualitative variables graphically. Today we are going to continue working on quantitative variables. So for quantitative variables, there are 5 basic summaries: frequency distribution, histograms, stem and leaf plots, Dotplots, and time series plots. So let's start off with the first summaries: frequency distribution for quantitative data. So here this is a data set of 65 vehicles. So if we follow what we learned from the last lesson to construct a frequency distribution, we're gonna have a table of around 40 numbers, more than 40 numbers. So it's not a good way to count its number to see how many times it appears on the dataset to construct frequency distribution. For quantitative data, we have to break the dataset into the smaller classes before we count its number. So here I'm going to use 7 classes. The first class from 0 to 0.99, 1 to 199, the third one 2 to 2.99, 3 to 3.99, 4 to 4.99, 5 to 5.99, and 6 to 6.99. So there are totally 7 classes. And then I'm going to start counting to see how many numbers in the first ranks appear on the dataset. So I figure there are 9 numbers between 0 and 0.99, 26 numbers between 1 and 1.99, 11 numbers between 2 and 2.99, 13 numbers between 3 and 3.99, 3 numbers between 4 and 4.99, 1 number between 5 and 5.99, and 2 numbers between 6 to 6.99. So here this is how I construct frequency distribution for quantitative data. So I repeat, for qualitative data, which basically just count its category to see how many times it appears on the dataset. But for quantitative data, we have to break it into classes. So that's how we construct frequency distribution. Similar to qualitative data, we also have relative frequency distribution for quantitative data. So to construct a relative frequency distribution for the data using the classes 0 to 0.99, 1 to 1.99, and so on, we basically follow the same rule that we learned from the last video. The relative frequency is the frequency over the total frequencies. So here we construct the relative frequency. We basically take its number, its frequency, divided by the total frequency. So 9 divided by 65 is 0.138, 26 divided by 65 is 0.4, 11 divided by 65 is 0.169, 13 divided by 65 is 0.2, 3 divided by 65 is 0.046, 1 divided by 65 is 0.015, and 2 divided by 65 is 0.031. So that's how we construct frequency distribution and relative frequency distribution for quantitative data. So I repeat, first break the dataset into classes, and then construct frequency distribution and relative frequency distribution. However, here you see here the choices of classes is up to us. So you are free to choose the classes. So different people with different choices of classes will end up having different distribution, frequency and relative frequency distribution. So the question is how to choose the classes. There is some definition. The lower class limits of a class is the smallest value that can appear in that class. The upper class limit of a class is the largest value that can appear in that class. The class width is the difference between consecutive lower class limits. And the requirements for choosing classes: every observation must fall into one of the classes. The classes must not overlap, and the classes must be of equal width. there must be no gaps between classes. For example, for the last example, we can choose the classes 0.00 to 0.99 for the first class, 1 to 1.99, and so on. Or some people can choose 0 to 1.99, 2 to 3.99, and 4 to 5.99, and 6 to 7.99. Or some people can even choose smaller classes 0.00 to 0.49, 0.50 to 0.99, and so on. So the procedure for constructing a frequency distribution for quantitative data is first choose a class width, then choose a lower class limits. For the first class, there should be a convenient number that is slightly less than the minimum data value. Step 3, compute the lower limit for the second class by adding the class width to the lower limits for the first class. So lower limit for the second class is equal to lower limit for the first class plus the class width. Step 4, compute the lower limits for each of the remaining classes by adding the class width to the lower limit of the preceding class. Stop when the largest data value is included in a class. Step 5, count the number of observations in each class and construct the frequency distribution. So here, histogram. This is a relative frequency distribution for particulate data. And now we are going to construct histogram. So what is histogram? Histogram is basically look like bar graph, but histogram is applied for quantitative data and bar graph is applied for qualitative data. So for frequency distribution, we basically first make a horizontal line and place the classes on the horizontal line and make sure there's no gap between them. They have equal class width, and then we make a vertical line represent for frequency, and we start making the boxes, the rectangles. Make sure there's no gap between them. So the difference between histogram and bar graphs is histogram there's no gap between rectangles, and histogram is applied for quantitative data. So similarly, we are going to construct relative frequency distribution and a relative frequency histogram for quantitative data. So exactly the same thing. First, we make a horizontal line and place the classes on the horizontal line. Make sure there's no gap between them. Then we make a vertical line and then build up the rectangles. Make sure the height of each rectangle is the relative frequency. So that's how we construct histogram. However, since we can choose different classes, so we are going to end up having different histogram. So how should I choose the number of classes for histogram? If we have too many classes, it will produce a histogram with too much detail, so that the main features of the data are obscured. If we have too few classes, it would produce a histogram lacking in details. So choosing a large number of classes will produce a narrow class width, and choosing a smaller number will produce a wider class width. For many datasets, the number of classes should be at least 5, but no more than 20. And for very large datasets, a large number of classes may be appropriate. So, for example, look at the two histograms for the same dataset. For the first histogram, we break it into so many classes. That's why the dataset become too much detail. And for the second histogram, we have too few classes. That's why the histogram lacking in details. So the histogram has some basic shapes. A histogram is symmetric if its right half is a mirror image of its left half. A histogram is skewed if one side or tail is longer than the other. So a histogram is long right-hand tail is said to be skewed to the right or positively skewed. A histogram with a long left-hand tail is said to be skewed to the left or negatively skewed. And here I have three examples. The first histogram is a histogram that is skewed to the left. The second histogram is symmetric, and the last histogram is skewed to the right. So different datasets have different shapes of histogram, but we have three basic general shapes of histogram: symmetric, skewed to the left, and skewed to the right. Most of a histogram, a peak or high point of a histogram is referred to as a mode. A histogram is unimodal if it has only one mode, and bimodal if it has two clearly distinct modes. For example, this is a histogram with two modes, so this is a bimodal histogram. Open-ended classes. Sometimes it's necessary for the first class to have no lower limit, or for the last class to have no upper limit. Such a class is called open-ended. For example, this is a frequency distribution for the age of people. So the last class we have no ending point. So we have 80 and older. So this is an open-ended class because we don't have the limit age for people. Some people might live up to 100 or even more. So we should basically have 85 and older, because if we make it 85 to 94 and so on, usually we don't have so many people live at that age. So we basically just combine them all into one single class that is an open-ended class. So this is 85 and older is an open-ended class. So for discrete data, when data are discrete, we can construct a frequency distribution in which is possible value of the variable forms a class. Then we can draw a histogram in which its rectangle represents one possible value of the variable. For example, this is a data set of discrete data because number of children cannot be a decimal. So this is a discrete data, and the way we make histogram is make sure there's no gap between histograms. So its number here is value number 0, 1, 2, 3, 4, 5, 6, 7, 8 should be at the middle of its rectangle. So again, for discrete data, the way we construct histogram is exactly how we construct bar graphs for qualitative data, but make sure there's no gap between them. And next, so we have finished histogram. Now we learn another type of summaries for quantitative data, stem and leaf plots. For example, here's an example. The table below presents the U.S. Census Bureau data for the percentage of the population age 65 and over for each state and the District of Columbia. So here we have a data set, and this data set is in decimal. For sure we can construct histogram for this data set, but we also can construct stem and leaf plots. So the way we construct stem and leaf plots is first we make a vertical list of all the stem in increasing order and draw a vertical line to the right of this list. Step 2, go through the data set and for its value, write its leaf next to its stem. Then for its stem, arrange its leaf in increasing order. So this is how we construct stem and leaf plots. First of all, we make a vertical list of all the stems in increasing order. And then we make a vertical line to the right of this list. And then we go through the data set and for its value, write its leaf next to its stem. For example, number 1 here means 8.1. So 8.1, 8 is the stem and 1 is the leaf. 90. So 90, that means 9.0. So 9 is the stem and 0 is the leaf. Here we have 10, 7, 2, 5. So we have three numbers, 10.7, 10.2, and 10.5. So 10 is the stem and 7, 2, 5 are the three leaves. So similarly, we have 11.5, 11.5, 12.0, 12.4, 12.7, 12.6. So that's the second step. Now we are going to rearrange the leaves in the same stem. So for the stem number 10, we have three numbers 7, 2, 5. So we rearrange them in increasing order. So we have 2, 5, 7, and do the same thing for the other stems. So that's how we construct stem and leaf plots. So stem and leaf plots also can tell you if the dataset is symmetric or skewed to the left or skewed to the right. So if you look at the dataset is lightly symmetric, Sometimes if you are given a dataset of all number in 2 decimal places, you cannot construct stem and leaf plots for a number with 2 digits after the decimal. So we need a technique called routing data for stem and leaf plots. For example, this is a dataset of 65 vehicles, and each of these numbers is a number routed to 2 decimal places. So if you construct stem and leaf plots using this dataset, if you use 1 as a stem, 5 and 0 become the leaves. So it's become very confusing. So we need to route them to 1 decimal places. So after we route the dataset to 1 decimal, we have a new dataset. This is the routed dataset, and we are able to construct the stem and leaf plot. So similar 0, 3, 5, 5, 6, 6, 9, 9, 9. That means 0.3, 0.5, 0.5, 0.6, 0.6, 0.9, 0.9, 0.9, 0.9. So that's how we construct stem and leaf plots. So again, if the dataset has more than 1 digits after the decimal, we need to route the data to 1 decimal place before we construct stem and leaf plots. Sometimes the datasets will not be in decimal numbers, but in whole numbers. For example, sometimes 1 or 2 stem contains most of the leaves. When this happens, we often use 2 or more lines for each stem. The plot is then called a split stem and leaf plot. For example, this is a dataset of all whole numbers. So to construct the stem and leaf plots, we don't have any number behind the decimal. So we are going to split the number. So for example, 58. So 5 is the stem and 8 is the leaf, and then continue for the other numbers. So we construct the stem and leaf plot. So this is called the split stem techniques. So that's how we construct stem and leaf plots. Similar to side-to-side bar graphs, we also have back-to-back stem and leaf plots. The basic purpose for this plot is just compare two information of the same class. So when two data sets have values similar enough so that the same stem can be used, we can compare their shapes with a back-to-back stem and leaf plot. In a back-to-back stem and leaf plot, the stem go down the middle. The leaves for one of the data sets go off to the right, and the leaves for the other go off to the left. For example, this is a back-to-back stem and leaf plot. So by these plots, we can have information of two variables at the same time for the same set of individuals. So this is how we construct back-to-back stem and leaf plots. First, we make the list of stem, the vertical list of stem. Then we make two vertical lines, one to the left and one to the right of this list. And then on the left side, we mark the leaves for one variables, and on the right side, we mark the leaves for the other variables. So that's what it's about stem and leaf plots. Now we go to dot plots. A dot plot is a graph that can be used to give a rough impression of the shape of a dataset. It is useful when the dataset is not too large and when there are some repeated values. For example, this is numbers of children of U.S. president and their wives. So to construct the dot plots, we mark the number on a horizontal line. And then for each number up here, we mark one dot. For example, number 0 here, we mark one dot at number 0. Then number 2, we mark one dot at number 2. And then number 10, we make a dot at number 10. And so on. So if we see the second 0, we make the second 0 on the top of the first dot. And make sure that these dots are line to line. So this is how we construct the dot plots. By the dot plots, we also can tell if the dataset is symmetric. The last plot of today is time series plots. So a time series plot may be used when the data consists of values of a variable measured at different points in time. For example, this is a time series plot for this dataset. So the horizontal line, the x-axis, represents for year, that means times, and the vertical line represents for the average. So this is how we construct time series plots. So that is everything for today. Thank you so much for watching, and I hope you guys enjoyed my video. So after that, I have finished graphical summaries for variables, both qualitative and quantitative. Next video, I'm gonna start working on numerical summaries for dataset. So hope to see you guys next time. Bye bye.